Okay, scalar and vector operation rules. Now, first of all, we haven't actually said what a scalar is. A scalar is just a number with no direction. So a scalar would be like the magnitude without the direction. Or A and B are both scalars because they're just numbers. Okay? So if you want, we can write that down. A scalar is just a number. No direction involved, okay? So that plays into this next thing. Okay, so these are just some basic operations. Suppose we have two vectors. Let's say we have vector A represented by component A1, A2. And let's suppose we have vector B represented by component B1, B2. And let's suppose that K is a scalar. Okay, let's suppose we needed to find K times vector A. What do you think that would mean we would do? Scalar, a number. So basically what I'm saying is we're multiplying a number times a vector. That would be done if you're increasing the vector. Do you remember doing, like, in geometry, doing transformations? And one of the transformations you can do in geometry is a dilation, where you're changing the size of something. Multiplying by a scalar would change the size of something, but not change its shape or direction. So that would be one application of multiplying by a scalar, would be keeping the direction but changing the magnitude. So all you would do is distribute the number through the components in the vector. So it would just be basically K times the first component and then K times the second component. Does that make sense? These are pretty simple rules. Do you want an example? Do you want me to go through all the rules first and then do some examples, or do you want me to do a quick example of each rule? All the rules and then some examples. Okay. Alright, what if we wanted to add vector A plus vector B? How would that be represented algebraically? Yeah, it's pretty intuitive, these rules are. A1 plus B1 and A2 plus B2. Good. Do you need me to even list A minus B? Probably not, because it's really easy. Okay, now here's the hard one, is A times B. This one is the important one to remember, and it is known as a dot product. By the way, if you go further in math in college, there's a class called linear algebra. And linear algebra is an entire college semester about vectors. Linear algebra was definitely not one of my favorite classes. We did a lot with matrices, a lot with vectors. Some of it was just really over my head, but it was required for my degree, so I did it. But I actually think I did well in it. I don't remember. It was okay. So, dot product is actually taking A1 times B1 and then A2 times B2 and adding those products together. That is known as a dot product. And that is going to be very important later when we learn something very important. Okay, so keep that in mind. Alright, shall we do a few quick examples, or do you think this stuff is easy enough you don't even need examples of it? What do you want me to do? Slide it down, like that? Like that? Okay. Do you need some examples then? Or do you think you follow? Maybe we should just do a quick example, make sure we understand. So let's say we have vector W at -3, 2. So that would be, if you start at 0, 0, the vector ends at -3, 2, right, on the graph. And vector Z, 5, -1. Okay, so if we wanted to do w minus z, what would that mean? What would we do? Negative 3 minus 5, 2 minus a negative 1, which gives us negative 8, positive 3. Correct? Okay, so that's subtracting two vectors. You also have adding two vectors. We're going to talk, so this is the rule for adding two vectors, although we're going to learn about another thing with visually adding vectors in just a minute, okay? All right, how about we do a dot product, shall we? How about we do w dot z? Then what? Negative 3 times 5 plus 2 times negative 1. And that's negative 15 plus negative 2, which gives us a final dot product answer of negative 17. Now you probably want to know, what does that even mean when it's related to vectors? Well, it is used in a formula we're going to learn today. Okay? So it will be important in a formula we're doing today. I know that when I was in linear algebra, I learned what it exactly means. It has something to do with the projection of a vector on another vector, and don't worry about it, basically. I'll stop there. How does that sound? Basically, if you have two vectors and you're projecting, you have, like, imagine a flashlight shining on one vector, casting a shadow on the other vector. It would change, the shadow would be a different length than that vector, but it would be going the direction of the other vector. Anyway, the dot product is related to that somehow. And in the old book we used to use, like 6 years ago, we had to actually learn that. But we don't have to anymore, so we're not going to worry about it. Is that okay? Okay. All right. Good. Okay, so those are our easy